So let's start now with the first concept in rectilinear motion, and that is displacement. Since the motion can only occur in one axis, so let's represent that with minus s plus s with this orange dotted line. It is the only axis along which the motion can occur, right? So at any time instant from origin O, the position of a particular point P can be described by this distance, and that S is actually the position coordinate of point P, right? Position coordinate, right? So this S is describing the position of point P or particle P at any given time instant t. So this is at some time instant which was t. So after a particular time, for example, after certain time called delta t, the position of that particular particle is changed and the new position is p prime, right? And the difference in the position coordinate is delta s, right? So the terminology or notation is very important here. Delta s is the change in position coordinate, and this is called the displacement of particle p, right? So this is displacement. So displacement is defined as the change in position coordinate between time t and t plus delta t, or in other words during the time interval delta t, right? So that was the first concept, displacement, change in position coordinate of a particle which is moving along one line only in this case, right? And then in the next case it will be moving in a curved path, and then finally will be moving in a three-dimensional path. Velocity is defined as the ratio of delta s over delta t, but that velocity will be the average value of velocity during that time interval delta t, right? So if you divide delta s with delta t, you will be actually getting average velocity, right? And let's represent it with v sub av, right? But if we apply the limit that delta t approach to 0, so if I apply delta s over delta t with limit delta t approach to 0, then that value of velocity will no more be average velocity, that will be actually instantaneous velocity, because now you assume that time difference between particle motion of p to p prime is very small, is approaching 0. So that will be instantaneous velocity, right? And we will be using the symbol small v for instantaneous velocity, and we know mathematically that when you apply this limit delta t approach to 0, that actually is the first derivative of s with respect to time. So we will be actually using ds by dt for instantaneous velocity, right? Another symbol which we will be using for that is v is equal to s dot, right? S dot is actually simply the first derivative of any quantity with respect to time, right? So if I say s dot, which means ds by dt, right? So again I would repeat, average velocity will be delta s by delta t, while the instantaneous velocity will be simply the first derivative of displacement with respect to time. A more convenient way to write the same thing will be v is equal to s dot. Similarly, the average acceleration will be average acceleration. Let's represent it with a sub av. That will be what? Delta v by delta t, right? Change in velocity of an object from point p to p prime divided by the time interval in which that change occurred, but that will be the average value of acceleration during that whole motion. But if we apply the limit that delta t approach 0, then that will be actually instantaneous acceleration. So let's write instantaneous acceleration. and let's denote it with small a, right? And that again will become a is equal to dv by dt, the first derivative of velocity with respect to time, right? So that again will be a fundamental relationship which you will be using again and again in this chapter. That can also be written as a is equal to d2s over dt square, which is actually the second derivative of displacement with respect to time, or in a more convenient way we can write it as a is equal to s double dot, where double dot means the second derivative with respect to time, right? So double dot means d2 of the quantity by dt square, the second derivative with respect to time. So all these relationships are like convertible, they are same thing actually in different notations and symbols. So that is also another form of the same relationship. Everything is clear. I think most of you are already familiar with these concepts from basic physics. If v is increasing, which means the rate of change of velocity is positive, right? If v is decreasing, acceleration is negative, the rate of change of velocity. We will sometimes be using the word deceleration actually for negative acceleration, right? One quick thing, and that is about the relationship between displacement, velocity and acceleration. We know that velocity is the derivative of displacement and then acceleration is the derivative of velocity. So there must exist a relationship to convert one into other two, right? So let's explore those relationships, and they will become your fundamental conversion relationships between these three motion parameters. So for example, we know that v is equal to ds by dt, and we also know that a is equal to dv by dt, right? So there must be a way to actually relate all three of them, right? What we can do from here is that we can write dt as ds over v, right? And from here also we can write dt as dv over a, right? And then we can equate them because both are equal to dt. So we will be actually getting ds over v is equal to dv over a, right? Or actually v dv is equal to a ds, right? So let's call that equation as equation 1, this one as equation 2, and what we did simply we solve 1 and 2 together and come up with another form of a relationship. Let's call it as like 3, equation 3, right? But we also know that a is equal to s double dot and v is equal to s single dot, right? We can put that also, that information also in equation 3, and then we will be getting as s single dot ds single dot is equal to s double dot times ds, right? So I replaced v and a and I write it in terms of displacement. So now this whole equation is in terms of displacement, right? So let's call that as equation 3 again. Let's call it 3a and let's call it 3b, right? Because they are actually the same equation. We are just writing acceleration and velocity in terms of displacement. So this is number 1, this is number 2, right? And then finally this is 3a, and another form of the same equation, let's call it as 3b, right? These are the fundamental relationships to convert one into other: displacement to velocity, velocity to acceleration, or similarly acceleration to velocity, and similarly velocity to displacement. So they are mathematical conversion relationships. By the way, these three equations, what is their form? Are they algebraic equations or exponential equations or trigonometric equations? What do you think? They have a specific form. Yes, please. Yes, they are differential equations, right? They have a specific mathematical form called differential equations, And in order to solve differential equations, you have to have a separate solution methods. Yes, please. Yes. So we have to solve them in a specific way, right? For example, if I give you acceleration and ask to determine velocity, you need to integrate acceleration to determine velocity, right? And similarly, if I give you the displacement of a particular particle and ask to determine velocity, you have to differentiate that, right? So the solution methods required to solve or to convert one to other will be actually coming from the theory of differential equations, right? So now let's see these relationships graphically also. They are here mathematically. You can convert one from other using the theory of differential equations. You can solve for velocity and acceleration for a given displacement, right?